because the small session is live and digital. Being local sources, global order, irregular.
Thank you. I would like to, first of all, I would like to thank the organizers, Nikolai Bashvit and Andrei Raygorovsky for inviting me to give a talk at this so auspicious conference. By the way, I appreciate very much the ability to invite other people from one country to Moscow in such a so-called time. It's very good experience. By the way, what the content of my talk will be dedicated to the model, mathematical model of crystal, and this mathematical model respects, corresponds better, reflects better the real state now in this very cold weather. It would be better than in July, for instance, because really this model of mathematical model of ideal crystal corresponds to the situation which precisely can happen only at the absolute zero temperature. So now we are closer to this temperature than in July. Okay. How to manage? Okay, what several pictures in the beginning illustrate the situation about situation in crystals, in the structure of crystals, and we are going to discuss some mathematical models and results about this stuff. What I usually say, certainly everybody knows that crystals form atoms, or crystals form one lattice, one integer point lattice, or several integer point lattices, and usually they say, okay, how this crystal receives a very high symmetry, like for instance lattice can have. Usually say, okay, atoms try to pack the space as dense as possible, and in result we get what is densest packing of space by walls by atoms, and this structure will be a lattice structure automatically. On the other hand, for instance, what this structure of the light, what for instance famous quartz, famous crystal quartz, is very special species of zeolite. But for instance, you see here the structure of zeolite, of quartz. And this structure doesn't remind us the dense packing. Really, you see here very huge emptiness, vacuums, and certainly the situation in crystals looks more complicated than what this very naive viewpoint. Okay, dense packing as possible. Okay, and we would like to study what is going on when you see. Okay, but let me say several more precise words. What is a crystal in mathematical viewpoint? Idea of this definition is due to Fedorov, and this idea reflected up to the last quarter of 20th century the situation in crystals very well. This idea was due to Fedorov. The definition was the following: first, a regular point set. Given Euclidean d-dimensional space, crystallography group, also G, this is some very special discrete subgroup of isometries of d-dimensional space, and some point x. Then the orbit of this point with respect to this group G is some discrete point set very uniformly distributed over space, and this point set is called regular point set, regular point system. Definition of crystal, mathematical definition of crystal, and it corresponds very well to positions of atoms in the real ideal crystal at absolute zero temperature. Definition of crystal. A crystal is a union of finite many orbits with the same, with respect to the same group G. Okay. Excuse me.
It is difficult to give a definition of crystallographic group because
okay, maybe on the next page. I will be definition of crystallographic group. Subgroup of isometries or motions in Euclidean space is called crystallographic if first any orbit of any point is discrete point set. Second requirement is that fundamental domain of the group is compact. Okay, now what is the fundamental domain of crystallographic group? What below you can see. What does it mean? The fundamental domain is a closed domain f of G such that for any point x, for this, for any point, for this fundamental domain contain the closure fundamental domain contains at least one representative of this orbit, and the interior of this fundamental domain contains at most one point from the orbit, from any orbit. Now, for instance, examples of fundamental domains. For instance, if you take in plane the abelian group generated by two translations in two linear independent directions. For instance, so let's take two linear independent dimensions. Let's take T1 is translation with respect along this vector and T2 along this vector. Then, and let's take the group generated by these two translations. We get an abelian group with two generators, and the fundamental domain in this case will be this closed square. Certainly, fundamental domain can be chosen by many different ways. For instance, you could take this fundamental parameter and so on. So we require that this fundamental domain should contain at least one representative from any orbit, and inside, in the interior, this fundamental domain intersects with any orbit at most one point. And we require definition of crystallography group. What the second demand is fundamental domain of the crystallography group, should be compact, must be compact. It means, for instance, like this parallelogram. But if you take, for instance, only group generated by only one generator, T1, then you will get again a new group which will be less richer, and the fundamental domain of this group is not compact. It is not crystallographic from viewpoint of dimension 2. Now, for instance, another example Another example of non-crystallography, discrete but non-crystallography group is rotation around some fixed point of finite order, for instance, rotation pi over n. Then fundamental domain will be this infinite angle pi over n. It is also non-compact, and this is not crystallography group. So, Hilbert, in his 18th problem, he put a question, proof or disprove that any in d-dimensional space, any crystallographic group has translational subgroup of finite index and Bieber-Bach. This theorem was proved for dimension 2. This theorem is not very hard. For dimension 3, this problem it was very hard, and the answer was obtained by Chantelis, and before 1900. And but Hilbert proved this problem to prove this theorem for any dimension. It was done by Bieber-Bach, and Chantelis Bieber-Bach theorem implies that a crystal, by further definition, is three-dimensional periodic structure. It is a union of congruent and parallel each other integer point lattices. Now, regular point set statement for the regular point set, the following conditions hold. First two conditions are conditions of definition of Delaunay set. There is such a small radius R that any wall in space, but here it is better. What I would like to say, what is a Delaunay set? Delaunay set fulfills the two conditions. First condition is there is such a radius R, R small positive, that balls centered at points of X with radius R don't overlap. They form some pattern. And another requirement is R, a capital condition, R positive, another value of R, another number R, is such balls form cover of space. Now, for instance, regular point set elementary approach. But the set X looks the same from any point X from X. This was such an interpretation of regular point set was given by Hilbert and Conforson. What does it mean? Well, for instance, let's take such a point set like this is a regular point set, and if we take this point and look at a point set from this point, and after that we move to any other point of the same system X and look from it at the same X, we will get the same picture. This is a definition. This is a definition. Another definition of regular point set. This definition was given by Hilbert and Conforson, but certainly this definition is absolutely equivalent to the group definition, as I mentioned 3 or 4 pages earlier. Looks the same. Looks the same. Okay, now I would like to pay your attention to the following question. Okay, crystals appear in the result of some physical process of crystallization. Okay, we start with some, for instance, with water, with some solution where atoms of future crystals swimming in very freely swimming, and After that, under mutual interaction between nearby atoms, these atoms stack together in some regular structure. And this regular structure has global order, has periodicity, has the same global order up to infinity. Why does it, I'm sorry, where from this comes from, what this global periodicity? No, Linus Pauling, Richard Feynman, and other physicists and chemists, they thought that periodicity of crystals appears as a result of recurrence in the crystal of local identical arrangement over and over again. Okay, local arrangement are repeated over and over again, and this recurrence causes global regularity of this structure. However, neither proof or no plausible arguments have been offered. And this question in 1970s became even more intriguing because, for instance, what discovered quasi-crystalline structures, pipe and rolls, and after that in laboratory conditions by Shackford, who received Nobel Prize only in 2011. It became known that there are another structures which are not periodical, but in which this recurrence, local recurrence, repeats over and over again. So, what the explanation by Pauling and Feynman becomes a little bit doubtful. One needs to one had to draw some frontier between periodicity and non-periodicity, which local conditions really imply periodicity and which don't. Well, this was a main goal of the local approach. What Delaunay in the early 1970s, he initiated this question, and first settings were proved by myself and Misha Stoden, his student also, and other contributors to this theory were, and late, Lagares, Clarence, Ludwig Danzer also, and Dolbilin and some other people. Okay, now, I would like to say, so, we take now, let's take some point x of our system x, or Delaunay set x, and let's consider a points which are closer to this point x, not actually closer than rho, than some rho. And let's denote also what such a neighborhood of points settlements. Neighborhood points in this neighborhood we call rho cluster at point x. For us it will be important also the symmetry of this cluster. The symmetry which leaves this cluster, which leaves this center fixed and move this cluster in its center. Let's denote this group by S of rho x. It is obvious that x, if x is a regular point set, then for any rho, for any positive rho, and for any 2 points x and x y, what these rho clusters of these 2 points are congruent. By basic local question is as follows. Vice versa. Let for some finite radius rho all rho clusters in a given point, in a given Delaunay set X. Let all rho clusters provide solutions. Is it true that from here, from this pairwise congruence follows the congruence of as big cluster as possible, and follows the regularity of this point set. This is the main was and is the main question of the local theory we studied during many years. Certainly, such a radius cannot be too small in terms of small and archaic. I will see you later. I will see some interesting questions. But here I would like to introduce another very important notion for us. Given Delaunay set, not regular Delaunay set, let the number and the row of congruent clusters in X is called it is called the numerator function. So if our point set is regular, is arbitrary, then one point X surrounded in one way, another point X prime surrounded in another way, and the third point X2 prime surrounded, for instance, in this, the same way like point X. And let's count all different classes for the given row. And denote this number by n of row. Certainly, in Delaunay sets, this number is infinite. But if, for instance, we consider Delaunay sets for which this number is defined and finite, then usually we say, after Lagrange, for instance, we say that this the point set is of finite type. So let's consider Delaunay sets of finite type. And for such Delaunay sets, n of rho behaves like here. For instance, between 0 and some rho 1, it is 1. After that, between rho 1 and rho 2, it is some other number, and this is a stairway like function having integer values, and certainly this function, generally saying, this function is growing. And for instance, if consider what Penrose type, then this function n of rho will grow asymptotically like O square. But in general case, it grows like exponents. And but if our x is an orbit, then this function, enumerator function, is always 1. If this function, if this x is a crystal, then the function grows to some constant m, and after that it goes to the infinity, being constant m. And what this case corresponds to the case of crystal consistent of m different orbits. Okay, now Okay, local criteria. This is what the first and basic, maybe basic theory in our theory was this one. A Delaunay set is a regular set if and only if for some value of radius rho two conditions hold. First condition is n rho plus 2r, n of rho 2 plus is 1, so all congruent, all rho plus 2r clusters are pairwise congruent. And second, very important study, the symmetry group of smaller cluster. But look this. Let it be. This is a rho cluster, and this is a rho plus 2r cluster. Certainly, there's any symmetry of this bigger cluster must leave invariant this smaller cluster, but not every this symmetry has to keep this bigger cluster. So usually this rho is bigger than rho plus 2r. Usually this is bigger. But assume as what on some step, for some rho, on second side. Then our cluster, excuse me, then our point set x is a regular point. Set. From here it follows the following corollary. Given dimension d, then there exists some constant dependent on dimension d and the ratio r over r small, such that if in some set x all clusters of the radius c are pairwise congruent, then all clusters for the bigger also are congruent, and therefore x is a regular point set. So the congruence of some classes of some fixed radius imply the regulator of this point set. And certainly basic problems here in this direction are as follows. To decrease as much as possible what this factor C d up for this factor C. And second, to release this C from this ratio R over R small. For D equal 2 and 3, it was done by Dolbilin and myself. And second, if there are any absolute constants C such that the zero congruence of some fixed radius rho clusters provides the regularity of this point set for any dimension. It looks plausible, but absolutely. What for instance, maybe there is such an answer or something like that. 10R, this condition n of 10R say it provides regularity of our point system. It is not excluded, but we are very far from proving this conjecture.
It's not that it constantly depends on R.
Excuse me?
But it still depends on R.
Yes. Certainly, this constant can depend on D, but maybe it cannot. Maybe it doesn't. But it is very possible that it doesn't. Okay, but for instance, a very simple claim one. Assume assume in X, let's consider in X let's consider in X clusters of radius to R. And this cluster has some group, symmetry group, which is denoted by this one. Then, if it is trivial, then it is enough to take, to require only the concurrence of all 4 R clusters in order to provide the validity of the whole set. But here, next point. Given a group G, a tower of this group is called the algebraic sequence of consistently embedded subgroups ending by the trivial group. G, G1, G2, Gk, which is equal to, which consists of just identity. The length K of the longest tower, really the given G has many different towers of different lengths, and the longest tower is length is called the height of our group G. Assume that our S of 2R, consider, okay, and assume, now let's take the height of this group, Then one can, from the main local theorem I cited, I quoted mentioned before, it's easy to see the following. Claim 2, that if, for instance, clusters of such a size h plus 1 times 2r form the single congruence class, then X is the regular point set. Now, I would like to mention more concrete results. For instance, in dimension 3, for instance, the radius 10R provides that X is a regular point. If 10R clusters are pairwise congruent, then everything is okay up to infinity. By the way, from any dimension D, what this constant to this factor cannot be smaller than 4. Why? What consider, for instance, if you consider such a condition, epsilon is relatively small positive number, and you require that 4R minus epsilon clusters are pairwise congruent. It is not enough to provide that our set is regular set. Why? But let's consider what such a lattice very narrow rectangles, and very high rectangles. A is much bigger than B. And the rho is 4R minus epsilon. But this A can be chosen by such a way that but this radius can be taken 4R minus epsilon. And you see,
because R in our case is what is the I in our case? R in our case is a certain radius of this rectangle. This is the R. And if you take this point and if you take it for R minus epsilon, it means what's the radius of such a size, and it contains this series of points from later, this and this, but it doesn't touch other rows. And in the result we get the following. Let's spoil this lattice by small shifts of these rectangles in each answer, in each second. For instance, here we move slightly to the right side. Here we move to the right side on the same length C, and so on and so on. This is a sequence of those all lattices. We get here, or this is a regular point set. If you take, for instance, this shift to the left, this shift to the left, and that shift to the right, the shift to the left, and to the right, then you get another point set which is also regular. But if you take one shift to the left, another shift to the right, and this sequence of R, A, will be very disordered, then our point set is non-regular point set. But anyway, in this disorder, if you take 4R minus epsilon neighborhood, this neighborhood will be the same in any point set as the regular one or in the regular one. So 4R minus epsilon doesn't provide regulated point set for 4R minus epsilon for A as small epsilon as possible. Now, I would like to say several words about the idea of proof of local theory. But local theorem is based on two lemmas. Lemma 1 on hammocks and swing. But assume you are in a swamp, and you stay in some hammock. I don't know, maybe Janusz, do you understand what is a hammock? Yeah. Yes? Okay, so you can explain it, because really I took it in this word from the dictionary, but I'm not sure if it is true. So you got hammocks in the set of hammocks in the middle of the swamp, and these hammocks form a small or capital Delaunay set. And if you can jump a small or capital, and if you can jump long distance to A, then you can save yourself, because you can because there is a sequence of these hammocks such that the longest side here doesn't exceed 2R. It is trivial lemma. It is trivial lemma. And now another lemma. Assume X fulfills two conditions of local theory. It means that rho plus 2R, rho plus 2R clusters are pairwise congruent, and there is some stability of symmetry groups. Then, what very important remark, observation. Assume tau some isometry which moves rho cluster of point x into rho cluster of point x prime. Then the same isometry moves bigger cluster, rho cluster R, into bigger cluster centered at another point. And what this is a proof, I think I should miss this point. Therefore, if I have time there, I will expose. But really, this is a very important observation for us. Now, we would like to prove the following based on these two levels. We would like to prove we have some point x, we have some point y, we have some point x prime and here y prime. Y prime, certainly y prime is here two-thirds. We have rho plus 2r clusters. We assume that all rho plus 2r clusters are pairwise coordinates. Therefore, there is some motion tau which moves x to y and eats this cluster into this cluster because they are pairwise coordinates. And now we would like to show that this tau moves the whole point set x into itself. And how does it go here? Let's link this point x to this x prime by some 2r plus. Now, okay, the 2r plus. And now, look this tau. If tau, let tau moves this rho cluster into rho cluster around the x1. Then by lemma 2, the same motion tau, assembly tau moves rho plus 2r cluster around x1 into this cluster. Now, this bigger cluster contains a small cluster around x1 because x1, not x1, because x1 is removed in the way from xx on the distance it moves to r. So what this cluster completely is contained in the rho cluster r cluster. Therefore, the same tau moves this cluster into this one. By lemma 2, this cluster, this motion moves the bigger cluster around x1 into the bigger cluster around x1 prime. And for this argument can be applied to consequently to the sequence x1, x2, x3, and so on along 1 to a path, what we want these two paths, and we can get in the result that on this point x prime by the same motion tau is moved by to some point from the same point set x. So this tau maps our x into itself, and one can say that it is true also convexly, and in the result we get regulated our point set x. Okay, what one needs to say is the following interesting fact. We noticed very recently okay, assume, but very interesting stuff. Assume our point Z is such that any S such that all 2R clusters are pairwise components. This is the first condition, and this cluster is semi-symmetrical. So this cluster is such that each point x prime has a minus x prime with respect to x to the center x 0. So then what this central symmetry around this point x can be extended to up to the symmetry on the whole point set x. And based on this observation, first theorem, one can get the following interesting fact, that assume our point set, the Delaunay point set x, is an arbitrary point in arbitrary dimensional space, R to the E. And assume all 2R spectral clusters are pairwise components. And assume they are central symmetrical. Then X is regular point set. It is a very interesting fact because, as I mentioned before, even for R minus epsilon is not enough. Here, 2R components of the components of 2R clusters implies regularity of this point set. Our example, I showed before. Our example was the following. You see, we had here a rectangle, here triangle, and our point set within this to our neighborhood was not center symmetric. And so examples which can be what the how to say morale of this theory is the following: that one needs to find counterexamples to our local theory for small radius rho. One needs to find only among sets which are not center symmetric. Now I would like to state only in the conclusion, I would like to mention one more theory. What we were talking about regular point sets. Really, there is analogous theory about all possible crystals. Crystals are defined as a union of several orbits. And Delaunay set is a crystal if and only if for some rho, two conditions follow. First, the number of clusters of some for some rho are stabilized only for this rho are stabilized. N of rho is equal to n of rho plus 2r. And for every EI class from this n of rho of k class of clusters, we have that their groups are stabilized. Then we get a crystal. And I would like also in my conclusion, I would like to stop on some open problems. What is proof that the components of 4R clusters implies that X is regular points system. Improve and do at least the weaker problem is improve an upper bound for dimensions 3. It looks plausible that one can, for instance, I have some proof of the following result. N of 8R is 1 implies regularity. But unfortunately, this proof is very, very technical and a lot of cases and takes a lot of pages, and I did publish it. Now, for any dimension d, equal or greater than 4, one needs to release this factor. To this factor, one needs to release from R and R. And for this very important problem, which has a relation to the topic Mark Weiss mentioned here. For dimension d, at least dimension d equal to 2, find the local conditions of x which guarantees that this structure of x is a quasi-crystal structure, like structure which appears from the Cantor projection method, or maybe from inflation-deflation knowledge, and so on. So it is ballpark problem. Okay, thank you very much. I think this is